film peak is quite broad. Basically, the film peak is trying to split. Okay, so this also signature that it has a mixture of different phases, and that is further confirmed by when we did the cross-sectional transmission electron microscopy. So this is a cross-sectional transmission electron microscopy for the BST20 and corresponding polar mapping showing like a mixture of the tetragonal, orthorhombic and rhomboidal phases. If we take the BST60, so this is for the BST60, so we can see has only single phases like a tetragonal phase. So now once we make the device, like out of plane device, this kind of device, and measure the capacitance and calculate the dielectric constant, we can see that the dielectric constant is very high for the BST20 compositions, which is around 30 to 1400, and reduced with the other compositions. And we calculate this dielectric tunability. We found this dielectric tunability for BST20 is almost 91%, reduced with the other compositions. And their frequency stability also pretty good for all the compositions. And once we measure this dielectric constant with the temperature, we found this the phase transition is very broad than the following the Curie-Weiss law. So like relaxer type of behaviors, and that is also further confirmed by our theory, like using the effective Hamiltonian model, and they also shows like a broad phase transitions. And once we check the temperature stability, BST20 particularly showing a very temperature stable until 500 Kelvin with respect to the other compositions. And we take these particular compositions BST20 and we grow a different thickness, and also we see that dielectric constant is enhanced with the thickness and tunability also enhanced with the thickness. And if we look at their frequency stability, the frequency stability also pretty good, all the thickness, and their temperature stability also pretty good for all thickness except we see in this 80 nanometers. Now summary of this work actually, so if we compare, so we have seen very high dielectric tunability for these particular compositions like a BST20, where we can see like a mixture of tetragonal, orthorhombic and rhomboidal phase, and if we compare with the existing literature for the lead free materials, we found our cases we really have a very high dielectric tunability as well as the breakdown voltage. So now question is, can we can we integrate with the silicon? So we grown these materials on silicon as well. We take the STO coated silicon and we grow these materials, and we can see this again the phase is single crystalline and surface you can see pretty smooth. And if we look at the full width half maxima from the rocking curve, which is okay, it's not so bad. And now this BST20 particularly, if we take the high resolution TM image and take the polar mapping, we can see again although on silicon it has also the mixture of tetragonal, orthorhombic and rhomboidal phases. And further we make the devices on these samples, and we found again the BST20 showing the high dielectric constant with respect to the other compositions, and tunability not high like STO, but tunability we found around 70%, and which is decaying with the other compositions. And again the phase transition is pretty broad for these compositions once we measure the dielectric constant with the temperature. Frequency stability is pretty good except the BST80, and temperature stability is okay for the BST20 with respect to the other compositions. Now we compare our data with the on silicon with respect to the other literature. So we found our cases the tunability is pretty high as well as the breakdown voltage. So now can we control the functionalities via the growth driven domain dynamics? So what we have done, so we take these particular compositions, calcium dope barium titanate, but also we checked the similar study on strontium dope barium titanate, but here I am showing only this calcium dope barium titanate. So what we have done, we check the domain structure change using this growth temperature, dielectric tunability also change with the growth temperature, and also another applications like electrocaloric effect also we have seen with the growth temperature. So we grow the materials on different growth conditions like a 630 degrees C, 670 degrees C and 700 degrees C. I don't know what is going on. It's okay, right? So then we check first the structure, and structure we can see is a single crystalline phase, but with growth temperature the stain is basically different, and which we want. And full width half maxima from the rocking curve is very good. The crystal quality tells that the film quality is good, and their morphology looks like also pretty smooth. Now once we look at the reciprocal space mapping at 103 reflection, so these materials grown on strontium titanate substrate, and we found that all films are relaxed, particularly the film which grown on 630 degrees C, which shows like a peak splitting, like a there is a AC nano domains, and this is further we confirm once we done the TM and polar mapping. So this is the cross-sectional high resolution TM image and corresponding polar mapping for 630 degrees C. You can see there is a lot of polar nanoregions like AC polar nanoregions, and this population is reducing when we are increasing the growth temperature like a 630 degrees C and 700. This 700 is going almost a C domains. And this is further we confirm through the phase field simulations, which is done by our theory collaborator Jijang Hong. And now we make the device. If we look at the first the dielectric tunability of dielectric constant and dielectric tunability, we found this 630 showing the high dielectric constant with respect to the other growth temperature. And once we look at the tunability, we found around 85 to 87% tunability for the BST for the BCT 630 grown at 630 degrees C, and reducing for the other grown on other temperature. And further we calculate this cumulative quality factor using these equations, so which is important for bias tunability as well as the efficiency under the efficiency of these devices. And we found interestingly the film grown on 670 degrees C showing the highest CQF values, almost 10 to the power 4 with respect to the film grown on 630 degree and film grown on 700 degrees C. So now we check this stability of this tunability stability with the temperature. We found they are all samples showing the good temperature stability. And if you look at the phase transitions, again the phase transition is pretty broad, but the transition temperature is enhancing with the growth temperature. And so this transition is showing like a diffuse type of behavior, and we calculate the diffuseness which is higher for the 700 degrees C, and which could be because at 700 the film grown at 700 degrees C could be arise defects, induce heterogeneity and partial strain relaxations. That could be because of this, that could be the reasons for this high diffuseness. So so can we link their polarization dynamics with potential applications like a solid state cooling or energy efficient thermal management? So for that we measure the electrocaloric effect, which is basically the reversible temperature change observed when we apply the electric field adiabatically. And once we do that, so what happens in generally in ferroelectric cases, if you apply the electric field, generally polarization goes, polarization is basically aligned, and if you take out the field, basically they have a hysteresis. Similar also can have the relaxer ferroelectric. So in the relaxer ferroelectric you have a polar nanoregions, and if you apply the field, this polar nanoregion is basically aligned, and this relaxer ferroelectric often show the stronger electrocaloric response over a wide range of temperature. So here basically we apply the electric field, we align the dipole, we change the entropy, and then temperature change, and that could be used for possible solid state cooling technology without compressors or refrigerated gases. And we measure that. For that, first we need to measure this P loop at different temperature, and we measure that, and using the Maxwell relations we calculate this entropy change, which is dP dt dE, and from that we can calculate this adiabatic temperature change using these equations. And rho is your bulk density, and specific heat capacity, CF this specific heat capacity, which is this for this particular materials. And after that we calculate, we found that the temperature change is highest for the film grown on 700 degrees C. Okay, and then we calculate the electrocaloric coefficients like using these equations, and also relative cooling power RCP, which is a product of delta T max like this, and the full width half maxima of this curve. And refrigerated capacity also we calculate, integrating the delta S response across the effective temperature span. And if we calculate all of these, and what we found that this electrocaloric coefficient is highest for the films grown on 700 degrees C, and also same also RCP and RC also is highest for the 700 degrees C. And we compare with the existing literature, we found this particularly 700 degrees C film showing the competitive value with the state of art lead-free electrocaloric materials. So summary of this study is basically by controlling the growth dynamics in the same material, we can have a high dielectric tunability, we can have a high CQF values, we can have a high electrocaloric coefficients. So now can we also design a morphotopic phase boundary through the compositional combinations? So we can take two materials and design such a way, can we also make this morphotopic phase, because this is the important where we can see most of high performance functionalities, and can this improve the functionalities. So we, in this motivation, so what we take this BCT and BGT, these two materials, and we mixture on differently, like a solid solution we make and make the thin films. So for example, x equals to 0, it can have a tetragonal phase. Now if we mixture like a 50-50%, it can have a morphotopic phase like a rhomboidal, orthorhombic and tetragonal phases. And if we go to the x equals to 1, we can have a diffuse relaxer type of phases. And how do we prove that? We grow this material, and then we did the TM image, cross-sectional TM, and for the first cases like a BCT, we're showing like a tetragonal phase, and then we go to the 50-50, and we can see this mixture of tetragonal, rhomboidal and orthorhombic phases. And once we go x equals to 1, we can see like a rhomboidal phases. So we can make this kind of morphotopic phase boundaries in these combinations. And then we check the structural study, again the single crystalline phases, and full width half maxima from the rocking curve is small, that means the film quality also pretty good. And we check the reciprocal space map, we found that they are all relaxed, particularly 50-50% has a peak splitting, that means it has a mixture of different phases. So that we can also confirm from the TM. Alright, now once we make the device, you can see that BCT, BGT, the 50-50%, you can see the dielectric constant is almost 6,000, it's pretty high. And once we calculate this tunability from this, we found is almost 98% at 1 megahertz frequency. The tunability also very high. So that could be used for many different type of applications. And also figure of merit also we calculate, which is basically the tunability divided by tan delta. And we found this 50-50% has a highest tunability, which has a very potential application, several cases. One may be the microwave devices. So now, can we also make this material in a such a way, can we stabilize the topological structures? Okay, so we make this material differently. Again, we can see the single crystalline phase, and this is a piezo force microscopy image out of plane. So like this is a BCT, this is a BGT, this is this is BGT, and this is BCT, and this is BGT. Sorry for the typo. So, and this is a 50-50%. So you can see these small bubble-like structures. So we are claiming this like as fermions, still not confirmed yet. We need to do a lot of TMs. And we check the fermion size, which is basically increasing with the compositions. Now, if we look at the fermion density, we found the fermion density is almost 20 gigabyte per inch square for the 50-50% cases. And I didn't go through very details about the topological stuffs. So this paper is coming out tomorrow online. So you can go through and check about more details about that. So summary of this work, okay, with this I would like to conclude of my work that we can grow this kind of materials like a BST, where we can achieve the tunability almost 91% and background field 800 kilovolt per centimeter. And we can also make the material such a way we can through the domain dynamics we can have enhancement of the electrocaloric response. Then also we can see we can integrate two type of materials and we can create the artificially this kind of morphotopic phase boundaries, and also we can stabilize the skyrmion-like structure in these lead-free materials. So, so here is my PhD work, PhD student who actually done all the work, and also I would like to thank all of my collaborators, who contributed in these works, and of course the funding agency like ISC, Bharat Electronics, and FIST. And before that, so whatever facilities I have in my lab, now I made all of the facilities as a user facility. So all over the country, anyone can book that facility and use it. Okay, so with this, I would like to thank you.
Thank you very much for the nice talk. So the session is open for the question answers.
Yeah, I can. Yeah, so related to the temperature change, this ferroelectric depolarization effect, right? You got the temperature change. So what is the estimation of this temperature change?
So for 700 degrees C, we see almost 10 Kelvin.
10 Kelvin.
So but if you look at the 670 or 630, so 630 showing is around 4 and 5.
So you have to fully polarize it and then make the field to 0?
Yes.
Okay, then.
Yes, so that's the thing we need to do it.
And how long it is there, this temperature?
So this is like relaxers. So still orientation is there. So the temperature dependent we cannot do it. Okay, but we did at the room temperature. That is the things we need for the applications. The room temperature, we see the temperature change is almost 10 Kelvin.
Any more questions from students? Okay, so if there are no more questions, let's thank the speaker again for a nice talk.